All right, let's get started. If you're going to be a telecommunications technician, really getting a handle on radio waves is, well, it's everything. It's the invisible world you'll be working in every single day. So today, we're going to build that foundation, piece by piece. So here's our game plan. We're going to start with the big picture, the electromagnetic spectrum, and then we'll drill down into the key properties that make these waves tick. After that, we'll see how we organize them using frequency and bandwidth. And finally, this is the important part, we'll connect all of it to the actual physical hardware you'll be installing and working with. Let's begin with the absolute basics. Every single wireless device you will ever touch, whether it's a phone, a radio tower, a satellite, it operates somewhere within this massive, invisible ocean of energy we call the electromagnetic spectrum. At the very heart of all this is the electromagnetic wave. Just picture a ripple of pure energy moving through space. It's got two parts that are dancing together, an electric field and a magnetic field, and they're always at right angles to each other. And here's the wild part. It doesn't need air or water or anything to travel. It can just go, even through the total vacuum of space. That's how we talk to satellites and spaceships. Now, you've got to remember, the full electromagnetic spectrum is huge. It includes everything from gamma rays all the way down to visible light. But for us, as technicians, we are laser-focused on one very specific, very useful slice of it, the radio spectrum. This is our playground. This is where all wireless communication lives. Okay, next up, let's get our terms straight. These are the core concepts, the technical glossary you're going to need to know to describe, measure, and, actually work with radio waves. So let's break them down. First up is frequency. The easiest way to think about this is just how fast the wave is vibrating. If a wave does one full up and down cycle in 1 second, we call that 1 hertz. Simple, right? If it does a billion cycles in 1 second, well, that's 1 gigahertz. So a higher frequency just means a faster vibration. Next, we have wavelength. You'll see it written as the Greek letter lambda. Now, this isn't about speed. This is about physical size. It's the actual measurable distance from the peak of one wave to the peak of the very next one. And here is the absolute key relationship you have to remember. As the frequency goes up, the wavelength gets shorter. They're complete opposites. And this little fact is going to be so important when we start talking about antennas. And then there's amplitude. This one's easy. It's just the strength or the power of the signal. Think of it like the volume of your voice. A quiet whisper, that's low amplitude. A loud shout, that's high amplitude. In radio, it's the same thing. A higher amplitude means a stronger, more powerful signal. Now, it's really crucial to understand that amplitude is completely separate from frequency and wavelength, totally independent. Frequency determines what kind of wave it is, and its properties, like how well it goes through walls. Amplitude just determines how strong that wave is. You can have a very strong low-frequency signal, or you can have a very weak high-frequency signal. They're two different knobs you can turn. Okay, so we've got a handle on frequency. Now let's talk about how we actually use it to organize the airwaves. How do we group these frequencies together to send all the data for something like a video call, or just loading a web page? Well, to keep things from being total chaos, we organize the radio spectrum into what we call frequency bands. A band is really just a specific slice, a defined range of frequencies. So, for example, when your Wi-Fi router says it's using the 2.4 gigahertz band, it means it's operating in a specific chunk of frequencies that regulators have set aside just for that purpose. So, how much data can one of these bands actually carry? Well, that's determined by its bandwidth. And there's a perfect analogy for this. You can think of bandwidth like a pipe carrying water. The more bandwidth you have, the fatter the pipe is, and the more water, or in our case, data, can flow through it all at once. It's that simple. More bandwidth means faster potential speeds. All right, this next part is where the rubber really meets the road. This is where we see how an invisible, theoretical concept like wavelength has a direct impact on the real, physical hardware that you're going to be installing on towers and rooftops. This is where theory gets real. And it all comes down to this one simple but incredibly powerful formula. Wavelength, that's lambda, equals c, the speed of light, which never changes, divided by f, the frequency. That's it. This little equation tells us exactly how to figure out the physical size of a wave as long as we know its frequency. Let's make that real for a second. Let's say you take a pretty common frequency, 1 gigahertz. If you plug that into the formula, you get a wavelength of about 30 centimeters. And I mean that literally. That's a physical, measurable size. You could actually take out a ruler and measure it. And this brings us to what might be the single most important principle for any technician. The physical size of an antenna is directly tied to the wavelength it's built to send or receive. A good rule of thumb is that an antenna works best when its size is about half the wavelength of the signal it's looking for. And you've seen this your entire life without even realizing it. Remember those old cell phones from the 90s with the long pull-out antennas? Those phones used 900 megahertz, which has a wavelength of about 33 centimeters, so they needed a big antenna. Your car's FM antenna is cut to a specific length for FM frequencies. And your smartphone today, it works at super high gigahertz frequencies, meaning the wavelengths are tiny, so the antennas can be small enough to just disappear inside the phone's case. So let's put this all together and talk about the practical application. Because as a technician, you are always going to be dealing with a fundamental choice, a trade-off between using high-frequency signals and low-frequency signals. And here's that trade-off on a single slide. On one hand, you have low frequencies. Their long wavelengths are amazing for coverage. They travel really far, and they're great at punching through walls and buildings. The downside, they can't carry a lot of data. On the other hand, you have high frequencies. Their short wavelengths can carry massive amounts of data, think super fast downloads, but they don't travel very far, and they get blocked by almost anything, a building, a tree, even your own hand. So how do modern networks like 5G get around this problem? Well, they don't pick one or the other. They get clever and use a layered strategy. They use low-frequency bands for that huge, wide-area coverage blanket. Then they use mid-bands for a good balance of speed and coverage in cities. And then they use those super high-frequency millimeter waves for insane speeds in really dense places like a stadium or an airport. But there's another amazing trick that those short, high-frequency wavelengths let us do. It's called beamforming. Because the antennas are so tiny, you can pack hundreds of them together into a single panel, which we call an array. And this array can act like a digital spotlight. Instead of just blasting the signal out in all directions, it can electronically focus a tight, concentrated beam of radio energy aimed directly at your phone. It gives you a much stronger, clearer connection and causes less interference for everyone else. And that really brings us to the big question, the final thought. Everything we've talked about today boils down to this one core challenge that you, as future technicians, are going to face every single day. Our demand for more and more data is basically infinite, but the laws of physics, they're fixed. So how will we keep balancing that constant need for widespread coverage with the never-ending hunger for massive capacity? That's the puzzle you'll be helping to solve. Thanks for tuning in.